it's recording now. Okay. All right. Yeah. Okay. So let's see. We're gonna move to the Lyquist stability criterion, right? Okay. So we're here. Yeah. In the last class, and we talked about how to evaluate the pole and zeros in the right and the left half plane, right? Okay. So you see that if you have a transfer function that carries a pole or zeros in the right and the half plane, and then if you look at its Lyquist plot, and the encirclement, we identify that it is that the encirclement around the origin on the G of S plane, that makes a difference, right? Okay, I hope you can remember the conclusion for those 4 cases, which is the left half plane, pole 0, and the right half plane, pole 0, right? Okay, simply to say is that if you have zeros in the left half plane, 0 and poles in the left half plane, then the Nyquist plot will not have any encirclement around the origin in the G of S plane. Okay, okay. If you have zeros and poles in the right half plane, then you're gonna see the encirclement around the origin on the G of S plane. Depends on if it is a 0, then the contribution is a positive 1. I mean, represents the encirclement is along the clockwise direction. Okay. Now for the pole case, the right half plane pole case, you're gonna see the encirclement is gonna be along the counterclockwise. So the contribution of a right half plane pole is gonna be the negative 1. Okay. So this is what we talked about in the last lecture. Okay. Okay. Yeah. Then we now need to, because this is just simply evaluation of the pole and the zeros. Okay, single pole and the single zeros, right? So now we're going to move to the general, case. Okay, you see, let's say if I have a transfer function, this G of S, it's in general format. So yeah, it's okay, because it doesn't matter what kind of a transfer function you're going to have. It's always the ratio of the 2 polynomials, the numerator polynomial and denominator polynomial, right? So if it is a polynomial, then I can always conduct the so-called pole 0 factorization. Okay, pole 0 factorization. Okay, right? Okay, see, in general format, okay, polynomial. Yeah, I know that for the causal system, we always have m is less than or equal to n. It does not exceed the number of n, right? So yeah, this is the causality, issue, right? So any physical system is a causal system. So we always have this cause. Okay. Now, so as long as you have the polynomial, I can always factorize my transfer function in the pole and the 0 format. Okay, it is just, you see, apparently because the order of the numerator is m and the denominator power of the denominator is n. Okay, so apparently I'm gonna have n0 and n poles. So this is what this indicated. The symbol pi, capital case pi, indicates the multiplication, the product, right? So we factorize the numerator into the zeros, the product, and the denominator into the poles product. Okay, m pole, m zeros. Okay, and so okay, yeah, okay, so yeah, since we have this pole and 0, then it is only matters only matters that we count how many zeros in the right half plane and how many poles in the right half plane. Is that right? I can do that. Once we do this conduct this factorization and find out the value of this ZIPJ, then I can easily identify how many right half plane zeros. And we're going to use a symbol Z to represent the number of right half plane zeros. Apparently, this Z should be less than or equal to M, right? Because the maximum possibility is that all zeros in the right half plane. Okay? Otherwise, it's going to be less than the, less than the M, right? So we're going to use a symbol Z to indicate the number of right half plane zeros. Okay? And then I'm going to use the symbol P to indicate the number of right half plane poles. And apparently, this P must be less than or equal, the maximum is N, right? Okay? So we just do the counting. Okay, then you're going to see that because each right half plane zeros is going to contribute 1, positive 1. So you have a Z, number of Z right half plane zeros. So the contribution is what? It's just equal to the, because each one count 1. And you have Z, the number of right half plane zeros is Z, capital Z. So exactly this right half plane poles will contribute a number that is Z. Okay? Represents that the Lyquist plot of G of S is going to encircle the origin on the G of S plane by Z numbers. And this is in clockwise direction, right? Okay? Simply accumulate the results for the single zeros case. Okay? Okay. Now, what about the P? Yeah, because we said that now we have a P number of right half plane poles. But each right half plane pole is going to contribute a negative 1. So you have a P number of right half plane poles. So the total contribution is going to be the negative P. It's going to be the negative P times, right? Okay? What does this mean is that those poles will contribute to the Lyquist plot of the G of S by P number of encirclement around the origin. But this encirclement is in the counterclockwise direction, right? Okay. So, yeah, what's left is the left half plane zeros and the poles. And we know that their contribution, both zeros and the poles in the left half plane, their contribution is what? Is 0. So I don't count those things. So now you can predict that in this case, the G of S, the Lyquist plot of the G of S, we're gonna have a net encirclement around the origin on the G of S plane by Z minus P times. Is that right? That's a very obvious factor. Okay? You have Z number of zeros, contribute the Z encirclement clockwise, and then you have a P number of poles, contribute the encirclement around the origin P times in counterclockwise. Okay, but they are in one single transfer function, right? So they cancel each other and to resulting a net encirclement around the origin. And this net number is Z minus P. Well, the only thing I'm not quite sure is that if the N, the net number of encirclement around the origin, is the positive number or is a negative number, or it's equal to 0. I don't know. Because you see, it depends on the number of the value of Z and P, right? Okay, so any case could be possible. Okay, if the number of right half plane zeros is more than the number of right half plane poles, then Z minus P what is a positive number. So you're gonna see the Nyquist plot of G of S, the total Lyquist plot, we're gonna have a net number n encirclement around the origin. And because z is larger than p, so n is larger than 0. So your net encirclement around the origin is going to be along which direction? Clockwise, right? Okay. Otherwise, if the z is less than p, which means that you have more right half plane poles, number of right half plane poles, than the number of right half plane zeros, then n is going to be negative. Okay? N is going to be negative. Okay, so this will indicate that the Lyquist plot of g of s is going to have a n number of encirclement around the origin, but this time it's going to be counterclockwise. So the number of n and its sign tells us a very clear conclusion about the net encirclement around the origin of the g of s plane. Okay, so if z is equal to p, that is possible. So that means that you have equal number of right half plane and zeros. Then what? Then you don't see any net encirclement around the origin. Okay, so based on this evaluation, let me erase that. Okay, based on this evaluation, every situation is included. Every situation is included. That's a hard factor about the general Lyquist plot of the transfer function. Okay, that's a general conclusion. Okay, it's always true. Okay, and it is as long as you have a transfer function, you get this conclusion. For example, you see, I give you an example here. Very simple example. Let's say if you have s minus 1 and s plus 1 and s plus 2 and s plus 3 and s plus 4. Then what? Then you just count. Oh, this transfer function has one right half plane zeros, which is this guy, right? So z is equal to 1. How many right half plane poles? Can someone tell me? How many right half plane poles? 0. Yes. Okay. Yeah. 3 right half plane? Are you kidding me? Mr. Imran? How do you count to the 3? Tell me why. Tell me. You probably didn't hear. They are all left half plane, right? Yeah, you see, they're all left half plane. You see, this transfer function has 3 poles at -2, -3, and -4. They're all in the left half plane, so there is no right half plane poles. Okay, okay. So yeah, so you have P is gonna be. You have P is gonna be why is always doing this? The P is gonna be equal to 0. Okay, so yeah, before you draw the Lyquist plot, you can predict it. You actually do not even need to draw the Lyquist plot. You can predict that the n is gonna be equal to 1, which means that if you draw the Lyquist plot of this guy, and then you're going to see net 1 encirclement around the origin. In what direction? In what direction? Someone, quickly. Clockwise. Yes. Yes. Okay. So you see, this is very nice. Okay. With this, principle, and it's very nice to help us, to predict what's going on for the Nyquist plot. Okay. And what I can tell you is that for the stability purpose, evaluation purpose, it is this encirclement that matters. The shape of the Lyquist plot does not matter. Okay, I don't care if it's a circle, I don't care if it's a square, I don't care if it's any other shape. I just need to make sure how many encirclement around the origin. Okay, it is the encirclement that matters. Okay, so now we understand the general case. Okay, so now we extend from the single zero pole zero case to the general case, right? Okay, so the conclusions here. Now we're going to apply what we established here, okay, to evaluate the stabilities of this closed loop feedback system, okay, feedback system. If you recall in the control one, I actually said many times, I said that, you know what, it is very important at, you know, to know what's going on for the closed loop system. This is the closed loop, right? But this is the open loop system, right? Okay, well, we assume that h of s is equal to 1, okay? We assume that h of s is equal to 1, okay? Without the loss of a generality, right? Okay, yeah, because you see, h of s represents the sensor, okay? So a sensor is, if we treat a sensor as a scale, then I can always scale it to the 1, to be 1, right? So I can assume that h of s equal to 1. Okay, then the g of s is going to be my open loop system. So in control 1, if you remember, I said it many times. I said, well, it would be better, you see, if we know the information of a g of s, which is the open loop system, then I can predict what's going on for the closed loop, right? Okay, I can predict it as long as I know the information of the open loop system, and then I can predict what happens for the closed loop system. The closed loop transfer function is this guy, right? Yeah, so it will be nice, you know, if we can have this kind of rules to be applied, okay? Yeah, here the Lyquist plot, plot, and provides such kind of advantages for us to evaluate the closed loop system's stability. Okay, let me make it clear. So here, my purpose here is that I'm going to use the g of s as a Lyquist plot. How to draw that? Yeah, we know how to draw it, right? So because it's a transfer function, we learned it, you know, so far, right? So based on the information of the Lyquist plot of g of s, I try to predict if my closed loop system, which is this guy, is stable or not. Okay, and this criterion is what we call the Lyquist stability criterion. You got my point? Right? Okay, so let's see how we can establish a relation between the open loop system's Lyquist plot and the closed loop system's stability. If I can establish such kind of a relation, I'm done. My job is done. And that's exactly what we call the Lyquist stability criteria. Okay? Now, so let's see. Let's see a couple of hard facts. Okay? Let's see a couple of hard facts. You got to pay attention to me, okay? From now, right now, okay? You got to pay attention to me because you got to follow me to make sure you understand the procedure here, okay? The evaluation here, okay? Otherwise, if you do not pay attention, you might get lost, okay? And you might get lost, okay? Okay, so now let's see what kind of hard facts we're gonna have. The first, yes, question? Okay, you don't need to tell me, James. You just need to pay attention, okay? Okay, now, first fact is that, you know, the zeros of 1 plus g of s are the poles of G, the closed loop system. Okay, let's see if this is true or not. Okay, the 1 plus g of s is zeros. Okay, that's it to me, okay? I'm not trying to, you know, play the game about the terminology here, okay? But unfortunately, we cannot avoid this kind of zeros and poles name, okay? So what is going to be the zeros of 1 plus g of s. Okay, let me write down the 1 plus g of s down here. See, because I assume that g of s is a ratio of 2 polynomial. So basically, you're going to have a numerator polynomial, you're going to have a denominator polynomial, b of s and a of s, right? Okay, so based on that, then I can construct 1 plus g of s as this. You see, the numerator of 1 plus g of s, apparently, this is a very simple, manipulation. It's going to be equal to what? B of s plus a of s. See? And the denominator of the 1 plus g of s, it's a of s, and which is the denominator of the g of s. So 1 plus g of s and the g of s, they share the same word, same denominator. But the numerator of 1 plus g of s is different. It's equal to b of s plus a of s. Okay, apparently, if you solve this numerator equation, that will give you the roots of this equation. Oh, I'm sorry. I missed the a here. Okay, I missed the a here. Okay, I missed the a here. So if you solve this polynomial equation, then the roots of this polynomial equation will be exactly the zeros of 1 plus g of s, right? Okay? Anyone disagree with that? I don't think so. Okay? This is so obvious. Okay, then let's look at it. If we have g of s equal to b of s over the a of s, now what is my closed loop system? Yeah, my closed loop system is here. So you substitute the b of s over a of s into this expression. Very easy, another easy manipulation will give you this expression. The closed loop system's expression in terms of the ratio of the polynomial. Okay, so now we find out that this time the closed loop system share the same numerator as the open loop system. Okay, share the same numerator, but the denominator becomes what? As plus b of s. Okay, so now you can see that. You want to solve the closed loop system's pole? Solve the closed loop system's pole? You're going to solve the same equation, right? The roots of this guy, of this equation, the roots of this equation, it's going to be both the zeros of 1 plus g of s and the poles of gc of s, closed loop system. Okay? Is it clear? Okay? Is it clear, right? Okay? Okay. So, second factor I've already stated, because I said that g of s and the 1 plus g of s, they share the same denominator. So that's why they share the same poles. But just be careful. These poles are the poles of g of s, which is the open loop system. So this is going to be the open loop poles. Okay? And they can be obtained by solving the polynomial equation as equal to 0. Okay? So these two hard facts hold. Anyone have any question about these two facts? No question, right? Understand. Okay, accepted, right? Okay, now we're gonna move to the critical part for the Lyquist stability. Okay. Well, you see, like what I said, because what we try to use is the Lyquist plot of g of s. But you know what? From this closed loop system, it seems that the denominator is 1 plus g of s. So here we're going to extend our evaluation of the Lyquist plot from g of s to 1 plus g of s. Okay. Okay, so here we're gonna, evaluate the Lyquist plot of 1 plus g of s. But this is okay. This is just another transfer function. If you know how do you evaluate the transfer functions Lyquist plot? That it doesn't matter which transfer function from this feedback control system, okay? You're gonna evaluate, okay? So to evaluate 1 plus g of s, it's okay. It's just like a normal, transfer function, okay? But you see, now I want to count the right half plane zeros of 1 plus g of s. And I'm going to indicate this number as the z. Okay. So is this 1 plus g of s Lyquist plot available? Yes, of course. Why? Because g of s is open loop system. Open loop system is something that we know. Okay, it's something that we know. So you can definitely draw the Lyquist plot of 1 plus g of s, right? Okay. Then if you can draw that, if you can have this expression of this 1 plus g of s, then of course you can count how many right half plane zeros it's going to be in this transfer function, right? So we're going to indicate that as the z. Okay, and I'm going to use the first factor here, because the zeros of 1 plus g of s are the poles of a closed loop system. So you want to count the number of right half plane zeros of 1 plus g of s. What does that mean? That means that this z, it indicates how many right half plane closed loop system poles, right? Same thing. It's the same thing, right? You see, I'm using the factor 1 here. Okay, so exactly this z actually is the right half plane closed loop poles. Okay, they are equal to the number of right half plane zeros of 1 plus g of s, right? Okay, now, yeah, I need to continue. So what is going to be the, why is always keep moving? So what is going to be the number of right half plane poles of 1 plus g of s? Well, we know that the factor 2 tells us that 1 plus g of s and the g of s, they share the same pole. So, okay, so this information can be actually obtained from the open loop transfer function g of s. So once again, it is available, right? So we're going to denote this number of right half plane poles of 1 plus g of s as p. Okay, so far so good. And then I'm going to predict what happened to the Lyquist plot of 1 plus g of s. We encircle the origin of the 1 plus g of s plane. You see right now, you see, I'm evaluating 1 plus g of s transfer function, right? So I have to evaluate it on the 1 plus g of s plane, right? Okay, it's just like you evaluate the g of s, you're going to count the encirclement around the origin on the g of s plane. Okay. So then this number apparently based on what we established before, right? Here I'm going to use the conclusion that we established here, a very simple fact. Okay, here. So I'm going to see that the net number of encirclement around the origin of the 1 plus g of s plane is going to be equal to z minus p times. Okay, yeah, you just simply apply that factor that we developed before, that we stated before, to the transfer function 1 plus g of s, then this conclusion holds. Okay, apparently, right? Okay, so the key words here is z. What is z? I've just said that. The z actually indicates the number of right half plane closed loop poles, right? See? I just said that this is z, okay? Actually, it is the number of right top plane closed loop poles, right? Okay, so now you want the closed loop system to be stable. What do you think the condition is going to be? Yeah, I've already said here. This Z number must be equal to 0, right? In other words, I should not see right top plane closed loop poles, right? This is what we learned from the control 1. When a transfer function is stable, no poles in the right top plane, right? Since this Z indicates the number of right top plane poles of the closed loop system, yeah, you want the closed loop system, you want this guy to be stable. This Z must be equal to 0. This is what we call the, well, actually, I need to make another revision here, right? This is what we call the Lyquist, okay? We call the Lyquist stability criterion. Question? In the first factor, Andre, hold on. At the end of, is it B of S, A of S equals 0? Yeah, well, okay. See, this I already state that. That's an error, okay? If the zeros or poles is on the S equal to 0 axis, yeah, you see, Andre, remember we said that if you do have zeros and, poles, zeros on the imaginary axis doesn't matter, okay? That one doesn't matter. But the poles on the imaginary axis, remember we said that here, you see, we're going to use the modified Lyquist contour to evaluate the Lyquist plot. And then as long as you use modified Lyquist contour, then all the facts that we stated later hold, okay? Because you see, eventually, when we use the modified Lyquist contour, we exclude all the imaginary axis poles to the left. We actually treat it as a stable one, because we know the stable one does not contribute to encirclement, right? So this way, if you evaluate Lyquist plot based on the modified Lyquist contour, all of those poles on the imaginary axis will not contribute to encirclement around the origin on the G of S plane. You got my point? Okay, right? Okay, so can we find the Z for any transfer function or only one H of S? Oh, Iman, it doesn't matter. You see, like what I said. Okay, I'm gonna tell you this. Okay, if the H of S here, okay, if you do not assume, let's say, come on. Let's say if you do not assume that the H of S is not equal to 1, then what happened? Then your closed loop system's denominator is 1 plus GH. Is that right? So yeah, your evaluation, it's gonna be on the 1 plus GH. What's the big deal? You just counting one more transfer function, right? Okay, so it's not a big deal. Okay, you know how to evaluate 1 plus G of S. When H is not equal to 1, you just evaluate 1 plus GH. Everything is gonna stay same. Okay, so that is why I said that here I can assume H of S equal to 1 without the loss of a general relativity. Okay, so if for a long unity feedback case, it's very easily to modify the criteria. You just need to replace the evaluation of the Lyquist plot from 1 plus G to 1 plus GH. Okay, in this case, you have to evaluate 1 plus GH. Okay, because that is the new denominator of the closed loop transfer function. Okay, you got my point? Okay, yeah. Any other question? Okay, so now we can move on. Okay, so you can see that yeah, you see, so exactly the Lyquist stability criterion basically says that if you have n equal to minus p, then what? Then your closed loop system will be stable. Okay? If you have this condition, okay? If you have this condition holds, then the closed loop system is stable. But how am I going to check this condition? Yeah, I just need to find the n. How am I going to find the n? Yeah, I just need to find out how many right-half plane zeros of 1 plus g of s. I said that this information is available if you know the transfer function model of the open loop system g of s, right? Okay, so this information, you can get it right away once you have the g of s, information. So how am I going to check the value of p? Yeah, that's even simpler. Why? Because you see, the g of s, the p is the number of right-half plane poles of g of s. Okay, right? So this information is also available if you know the transfer function model of g of s. So you can see both information, you can actually get it from the information of the g of s. Not the g of c, g sub c, not the closed loop. You don't need the closed loop transfer function, okay? You don't even need to know what kind of closed loop transfer function is going to be. You just need to know the information of the g of s. Then you can predict that if you put this kind of open loop system into this feedback structure, if the closed loop system will be stable or not. Is that nice? That is very nice. Okay, that is very nice. Okay, you don't even need to derive the closed loop transfer function. Then you know the closed loop transfer function is stable or not, right? Okay, so this is why the Lyquist stability criterion is applied in the control very broadly. Okay, because people like it. Okay, now if you recall what we talked about in the control one, okay, you remember we define the closed loop the transfer functions poles in the left half plane to be stable. Now in control one, we introduce one criterion for the stability check. Someone can, if you remember that, what is that criterion? Yeah, Rose-Hurwitz criterion, right? Rose-Hurwitz criterion, right? But if you recall, the Rose-Hurwitz criterion is actually a criterion applied to evaluate a polynomial's roots, right? It can be applied to evaluate how many roots in the right half plane for a polynomial equation. That's what the Rose-Hurwitz criterion says. Okay, because it's only evaluate the denominator, the polynomial. So in order to apply Rose-Hurwitz, you know what? You need a closed loop transfer function, because you need to know what is going to be the denominator polynomial of the closed loop transfer function, right? Before you have that information, you won't be able to use Rose-Hurwitz criterion. Okay, what does that mean is that in order to apply Rose-Hurwitz criterion, you do need a closed loop transfer functions information. That is the biggest difference, fundamental difference between the Rose-Hurwitz stability criterion and the Lyquist stability criterion. Okay, which one you prefer? Apparently, you're gonna like the Lyquist stability criterion better, right? Yeah, you see, apparently Lyquist stability criterion is much better. Okay, I don't even need to derive the closed loop transfer function, right? Okay, so that is the key point, that why we want to talk about this Lyquist stability criterion. Okay. Yeah. So yeah, let me see if that example is still here. Yeah, you see, for this example, okay, let's say if this is your g of s, and then you put this g of s into this closed loop the feedback structure. Can someone tell me, will the closed loop system stable or not in this case? Can someone tell me? You see, based on the Lyquist stability criterion we just stated, this is the example. Okay, you're gonna have a g of s is equal to this guy. Okay, so can you tell me if you put this guy here, will the closed loop system stable or not? Not stable. Yeah, of course, right? Because we just find out that this one does not hold. You see, this condition does not hold. Okay, this condition does not hold, right? You see, we know, because in this case we know z is equal to 1. Actually, we know z is equal to 1. Okay, it's right half plane zeros, right? Okay, and we have p is equal to 0. So n actually the net encirclement is going to be 1, right? So apparently, okay, see, you see the advantage right away, right? Okay, I just need to see the g of s as the expression. That I'm telling you, forget about it. Okay, you put this system here. Okay, you put this open loop system here to construct the feedback control. The closed loop system will not be stable. So forget about it. Don't do that. Okay, right? So this is really nice, criteria. Okay. Okay. So any other question? Yeah. So we need yes. That is the condition that should be satisfied, right? Okay. For the closed loop system to be stable, right? Okay. So now let's go further. Yeah, I can summarize the procedure to apply the Lyquist stability criterion here. Okay. The procedure is this. Okay. Procedure is this, right? Okay. See, first, given the g of s, now this transfer functions information should be available. Okay. You have to know this transfer function. Okay. Now, first step 1 is that you're gonna find the p from the open loop system's information. Okay. Find the p. P is what? Yeah. Number of right half plane poles of g of s. Right. Okay. This is open loop pole. This is open loop right half plane poles. P is not equal to 0. It's okay, because the open loop system, I don't care if it is stable or not. Okay. It could be unstable. Okay. Now, then second, step 2 is that, okay, you're gonna draw the Lyquist plot. Okay. The purpose to draw the Lyquist plot is that we want to find the information of n out from the plot. Okay. Right. Well, I don't care about the shape. Once again, I only care about the encirclement. You see, this n. This is going to be, once you draw the plot out, this n is going to be the net encirclement around the origin, right? Okay. So yeah, this is a perfect information that we needed. So we can identify m from the plot. Now, then, yeah, you just need to be careful. The sign of the n is gonna depends on the encirclement. It's around the origin of 1 plus g of s plane. It's a clockwise or a counterclockwise. Will you be able to do that? Yes, of course, you can do that. Once you draw the plot, you know the direction. Okay, so you can easily figure out if n is larger than 0 or negative or less than 0. Okay, so now you have the information of p and you have the information of n. Okay, what you need to do is what? To verify n plus p. You know what? See, carry the signs of the number, right? Because the p can only be positive. P can only be positive, okay? P can only be positive. P cannot be negative. I mean, what do you mean by -2 number of right half plane poles of g of s? That doesn't make any sense, right? So p is always positive. But n could be positive, could be negative. Depends on the direction of the Lyquist plot. Okay, encirclement around the origin. Okay, so you verify n plus p. If this number is equal to 0, yeah, no problem. Closed loop system is stable. Otherwise, if n plus p is not equal to 0, then the closed loop system is not stable. You got my point? Okay. You see, this is actually a very straightforward factor. It's that, because p can only be larger than or equal to 0, right? Okay. So you want the closed loop system to be stable. You know what? N can only be less than or equal to 0. It cannot be positive. Okay? Okay? You got my point? Okay? It cannot be positive. Okay? If n is positive and p is not equal to 0, then what? Then this n plus p is not going to be equal to 0. Okay? It's not possible to be 0. So you can see the encirclement, cannot be clockwise. Okay? So it needs to circle counterclockwise to be stable. Yes, that's right. Okay? Right? Okay? So this is very easy to tell. Okay? Very easy conclusion to tell. Okay? N must be less than or equal to 0. It cannot be positive. Okay? Okay. So now, you see here, we are evaluating the 1 plus g of s. But then you're going to say that, because we already know the g of s, and the 1 plus g of s and the g of s, the difference is only 1. So why not just stay with the g of s plane? Why should we, talk about 1 plus g of s plane, right? Yes, you can do that. You see, we can actually only stick with the g of s plane. However, you got to be careful. Because what? Because the origin of 1 plus g of s plane actually corresponds to the point minus 1, 0 point in the g of s plane. That's a simple, factor. You see, you have the g of s, and then you have the 1 plus g of s. This is 2 plane, right? Okay. So now you have the origin on the 1 plus g of s plane. Well, this means that 1 plus g of s is equal to 0, right? If 1 plus g of s is equal to 0, then g of s must be equal to -1. So if you want to plot this on the g of s plane, then this point, this origin is going to be right to stay at this point, right? See? This factor is very easy to be established. Okay? So, you know what? Basically, this says that you just need to make a little bit of modification, okay? Do not pay attention to the origin. Instead, pay attention to the point -1, 0 point. Then what? Then you don't need to, you can throw the 1 plus g of s plane away. You only need to talk about the g of s. Okay? See, eventually we find out that, I don't even need to mention 1 plus g of s. Okay? I don't even need to mention 1 plus g of s. Everything can be done for the g of s. Okay? So, this point, from now on, you should keep that in your deep mind, okay? It is gonna be very, very, very important, okay? Always that we evaluate encirclement, it's around the -1, 0 point. This point is so critical, okay? Because it basically determines the stability of the closed loop system, okay? So you have to keep this point in your very deep mind. Never forget it, okay? Never forget it. -1, 0 point on the open loop transfer functions g of s plane, okay? -1, 0 point on the open loop transfer function g of s plane. So, as long as you shift your encirclement from the origin on the 1 plus g of s plane to the -1, 0 point on the G of S plane, then whatever we said before applies. Can be straightforwardly carried. Okay, see, the procedure now is going to be modified just slightly. Okay, you see, first find the P, yeah, from G of S. Okay, you can do that. Second, you see here, you don't draw the Lyquist product of 1 plus G of S anymore. You just draw the Lyquist product of G of S. No big deal. But you know what? The encirclement is going to be counted around the -1, 0 point. Okay? And you still find the information of this n, net encirclement, around the -1, 0 point. Again, it could be positive, it could be negative. And then check if the n plus p. So you see, everything stays. Everything stays except for that the encirclement is going to be evaluated around the -1, 0 point. And then you play only the G of S plane, not the 1 plus G of S plane. Okay? So yeah, this migration is going to be very easy. Okay? Migration is going to be very easy. Okay. Go further. Actually, you know what? I said many times, and normally when people design a physical system, nobody intentionally try to make it an unstable system. Okay, nobody intentionally try to make it unstable. Okay, instead they always like to design it to be a stable system. Okay, so this is a very hard factor. Okay, this is a very easy to understand. Okay, I mean, unless you don't have a choice. For example, I mentioned several examples. Is you see car. Let's say car is moving on the ground. Were you gonna design a car that cannot stay on itself? It's gonna roll over if you put it on the ground. You don't want that. I mean, nobody wants that, right? So apparently, if you design a car, it has to be stable. Unless you don't have a choice. What kind of a system you don't have a choice? Can you give me an example? What kind of a system you design and it has to be unstable that because you don't have a choice? Can you give me one? Okay? Can you give me one such kind of a system? Someone? Can someone answer my question first? A system with 0 poles in the right-hand plane? Okay. Andre, how about a plane? Airplane. You see, you fly an airplane, the flight dynamics itself is not stable, right? Unless you add a flight control. Okay, you're right. You see, because the plane, cannot stay on itself in the sky because it always fall. Okay, right? Very easy to understand, right? And also, how about the inverted pendulum? That's even simpler system, right? The inverted pendulum, the upward position, that position is not stable, right? Okay, if you touch it and it will fall. So inverted pendulum itself is not going to be stable, right? Okay, so that's unstable. That system, you don't have a choice because it's an inverted pendulum. If you make it stable, that is not going to be an inverted pendulum. That is going to be a pendulum. The bar is going to be to the downward position, not the upward position, right? So the upward position, if you look at the model, it's not. It's going to be an unstable, model. Okay, so because you don't have a choice, right? So yeah, we do have certain kind of physical system that is not stable inherently, okay? Because we don't have a choice. As long as we have a choice, we will always like to design our physical system to be stable, okay? So because of that, so yeah, we like to have a simplified case, okay? You see, is that now I assume this G of S open loop system is what? It's a stable. Okay, yeah. You see, this is the stable case can be easily derived because if an open loop transfer function is stable, then the P is what? Is 0, right? The right half plane pole is 0. Then you're based on the equation MPZ. In this case, A will be always equal to Z. Okay, because N is equal to Z minus P, right? Remember? So if P is 0, then you know what? You're gonna always have N equal to Z. Okay, so in this case, if your open loop system is already stable, then the Lyquist stability criterion actually can be very simple. Okay, it's just you know what? You evaluate the Lyquist plot of G of S, and this Lyquist plot should not have any encirclement around the -1, 0 point. Very simple, right? You see, N must be equal to 0. Okay, if you see the encirclement happens, then the closed loop system will not be stable. Okay, and you know, based on the assumption that the open loop system is stable. Okay, so this is simplified. You know, like what I said, because most of the physical systems are stable. So this is in practice, it is actually this is simplified Lyquist stability criterion. You know, applied. You know, very broadly. Okay, so but it's okay. Both cases, you know, you can still use the general case, right? It doesn't matter. It's just the difference is just the P is equal to 0 or not equal to 0. Okay, so either way is fine. Okay, but you know, many times when you talk about the Lyquist stability criterion to other people, they always mention that, oh, I should not see any encirclement. Okay, when they say that, they imply that the open loop system is stable. Do you know that? Okay, okay. When they say, oh yeah, I don't see the encirclement around the -1, 0 point. Okay, so the closed loop system must be stable because they imply that the open loop system is stable. Okay, they just don't mention that, right? Okay, otherwise, if the open loop system is not stable, then that conclusion does not hold. Okay, that conclusion does not hold, right? Because we need N actually must be equal to -P. Okay. Actually, we need to see encirclement around the -1, 0 point counterclockwise to guarantee that the closed loop system to be stable. Okay, so yeah, so I think that you should have no problem to understand the difference between these two, right? Okay, so yeah, any question about that? Okay, so now we already established the Nyquist stability criterion. In all those cases, we assume H of S. Yeah. Like what I said, Ali. You know, I mentioned, you know, just now, right? If H of S is not equal to 1, you replace G by GH. That's it. You replace G by GH transfer function. Okay. Okay. Then you evaluate GH transfer function, not the G, right? Okay. Not a big deal. The nature of the transfer function does not change. You agree with that? Right? Okay? You got my point? Okay? Yeah, so that is why I don't even mention, you know, the H of S is not equal to 1 case. Okay? You know, because you can get it easily. Okay? Derive it easily. Okay? Any other question? Any other question? Okay. So Abraham, I see your question. If we are given, do you want me to answer? You still have this question, Abraham? Okay. If we are given a Nyquist plot, how do we find? Oh, Abraham, you know, if you use MATLAB to draw it, and you know, and MATLAB will show you the direction. And also, if you recall, you know, when I talk about the polar plot, see this one, the Lyquist plot. Okay, go here. You see the Lyquist contour. The S is specified along the clockwise on the Lyquist contour, correspondingly, the Lyquist plot will have carrier direction. Okay, okay, because this is the mapping, right? So point-to-point mapping. So if you have the direction on the Lyquist contour S for the S, then you should have the direction on Lyquist plot. Okay, so that direction can be easily determined. Okay, it depends on the how you move the S. The point on the Lyquist plot is going to move, right? Okay, okay, yeah, okay. Always be given G of S. We as well, yeah, you see, that's a good question. I mean, from the statement of the Lyquist stability criterion point of view, I always assume G of S is available, right? You are given the information of G of S. But you know what? I can tell you what's going on for the Lyquist, plot of G of S, and then ask you to tell me what happens to the G of S, right? So it's just like you have three quantity, and you know two of them, you can solve the third one. But which two of them you know? It could be arbitrarily too, right? So do not be too stubborn and say, oh yeah, I need to be given the G of S. But you know what, in the examination, I probably intentionally not give you the information of the G of S, and then give you the information of the Lyquist plot, and ask you to deduce the information of the G of S. Can you do that? You should be able to do that, because this is all based on the principles that we talk about here, right? You see what I mean? Okay, so do not be too stubborn. You say, oh, it's just remember, oh, I have to be given the G of S, otherwise I cannot do anything. No, depends on the information that you are given, right? If I give you the Lyquist plot information, yeah, ask you to deduce the information of G of S, are you going to say, no, I don't know how to do it? That you have to know how to use this criterion principles flexibly. You got my point? Okay, so it is very important to understand the relation here in this principle. Yeah. Okay, you know the trick, Abraham, right? You see, in the examination, yeah, there are many tricks I can play, right? Okay, I can give you this condition, I can give you that condition, and then ask you to do it. But in any case, I will not only give you one condition, one information, and then ask you to deduce two. That won't be possible. Okay, that will be many possibility. That is not good, right? Okay, do we establish that a clockwise encirclement means unstable, and counterclockwise encirclement means stability? Well, you see, Danilo, it's based on the condition, right? But all I can say is that if you see the counterclockwise encirclement happens, then the stability is possible, but not necessarily it will be stability, because counterclockwise encirclement is a necessary condition, but it's not a sufficient condition, because you need to match that n equal to minus p. You see what I mean? Okay, if that condition is not matched, then even if you see the counterclockwise encirclement, the system could be still not stable. You see what I mean? Okay, okay, Danilo, you got my point? Okay, so do not, this is another stubborn case, okay? Do not be stubborn, oh, I just need to remember there should not be the counterclockwise encirclement. No, do not forget the other condition, n must be equal to minus p. That condition should be satisfied too. And that condition can only be satisfied by the counterclockwise encirclement. Okay, so that is why I'm saying that counterclockwise encirclement is a necessary condition, but not a sufficient condition. Okay, so you have to check the that equations further. Okay, to make sure the closed loop system is stable. Okay, okay. Yeah. Any other question? No more, then we're gonna move. Okay, so what time is? Okay, yeah, I still have several minutes. So okay, so let's move on. Okay. See the good things, for this Lyquist stability criterion is that it is not only can allow us to tell the closed loop system stability, but also it actually gives us a way to define the so-called stability margin, okay? And that is a very nice application, okay? The margin means that how far your system is going to be away from the stability. And that would be nice, right? Okay. You see, not only you know the system could be stable, but also you know how far this guy is from the unstable boundary. That would be nice because that will give you a margin to play. Okay. You can use, because once you have the stability margin, then you actually have the redundant of stability. Okay. You have more than the requirement for the stability. Then people always talk about this. Oh, since I have the redundancy here, then can I use the redundancy for other purpose? The so-called optimal control is derived here. Okay, because the optimal control is actually an application of the stability redundancy. If you do not have the stability redundancy, then you have no choice. You have only single choice. You have no multiple choice. If you do not have a multiple choice, how you can talk about the optimal control? The optimal control is the one that is the best one within many controllers. But as long as it is a controller, it should satisfy the stability first, right? I never talk about a controller that make the system unstable. That kind of a controller should not be my candidate, right? But since you have the redundancy of the stability margin here, that means that there must be many controllers satisfy the stability requirement. Then it gives me the base that, okay, I can do the optimal control to pick up the best one, right? But you know what, unfortunately, how to pick up the best one, there are many ways to pick up the best one. So how to pick up the best one out, it is not the same unfortunately of this course, okay? So if you want that, and you have to go to the graduate study, okay? So if some of you interested and try wants to follow me to go for a graduate study, yeah, you can go for it. I will tell you how to pick up the best controller within many stabilizing controller. Okay. So yeah, but for the traditional method on the time domain, it's going to be very hard to characterize this margin, stability margin issue. So the Lyquist stability criterion actually has a lot of advantages to tell us how we can establish a very important concept that is called stability margins. Okay, and specifically, this stability margins is classified as the gain margin and the phase margin. Okay, and another condition I need to state it here is that anytime when we talk about the stability margin for the closed loop system, I mean that the open loop system must be stable. Okay, no argument here. Okay, I only means anytime when I talk about the stability margin, in other words, the stability margin can only be stated for a stable open loop system. If the open loop system is not stable, you first design the controller. I mentioned it in the control one, right? Your first purpose is to design the controller to stabilize it. Okay, to stabilize it first. You see, it's just like the airplane. Okay, see, you want to make the plane fly better, you have to first guarantee that the plane can stay, the airplane can stay in the sky stably. What does that mean? That means that you have to have a base controller to first stabilize the plane in the sky. Then you can talk about how I'm going to manipulate the plane in the sky. You see what I mean? If the plane, can only drop, cannot stay stably in the sky. Well, you're going to talk about, can I roll the plane? Can I, turn the plane? Can I, climb, make the plane climb? You have no way to talk about the other, performance. You see what I mean, right? So in this sense, we only, we only talk about the stability margin issue for a stable open loop system. Okay. So clear. Okay. So we are in agreement. So the following statements are all built based on the assumption that the open loop system is stable. Okay. Now we need to go back here, because if the open loop system is stable, then we found out that the Lyquist stability criterion actually can be very simple. It's just simply I should not see any encirclement around the -1, 0 point, right? Okay. If the closed loop system wants to be stable, then there should be no encirclement around the -1, 0 point, right? Okay. You see here we establish here. Okay. Then we are using this factor to derive the so-called gain margin and the phase margin. How to do that? This is the case, okay, in this picture. Okay, see, this blue line is what we call the Lyquist plot of G of S, okay? -1 point is here, okay? Okay, so assume that, yeah, you already draw the Lyquist plot like that, okay? And also, in order to evaluate the stability margin, we're going to concern about the two crossover points. One crossover point is that where this Lyquist plot is going to cross the real axis of the G of S plane. This is the G of S plane, okay? This is the G of S plane. So we're gonna concern about where the Lyquist plot of a G of S cross the real axis. This is the first crossover. Second crossover is here. See, that's the crossover between the Lyquist plot and the what? And this unit circle. This is a unit circle, okay? You see, -1 point here. This is a unit circle. So this unit circle is going to pass through the -1 point, right? Apparently, okay? Okay, so once you capture this two crossover point, then we can talk about stability margin. For example, you see, if you make a K multiply by G of S, what do you think this K is a constant value? What do you think this K is going to affect the Lyquist plot? Yeah, it's going to expand the Lyquist plot, right? Oh, yeah. If it is expand the Lyquist plot, depends on the value of K, right? If K is larger than 1, then you know that because you multiply the K to the G of S, so this is just like you exaggerate the magnitude of the G of J omega, right? So you exaggerate the magnitude, that's just like you expand the plot. Otherwise, if K is less than 1, then you're going to be shrink in the Lyquist plot. Okay, so because the K does not change the phase of the G of S, right? It only affects its magnitude, does not affect the phase of the G of S. So what do you think this crossing point is going to be? When you apply a K is larger than 1, what do you think of this new crossover point, for the K G of S is going to be? If K is larger than 1, this point, where this point is going to move? Can someone tell me? Yes, move to the left, right? Yeah, you see, very easy to figure out. Why move to the left? Because only magnitude change. Phase does not change. You see, the phase of this point is here. It's minus, or if you measure from here, we always like to measure from here. So it's going to be the -180 degree, the phase. And this phase does not change. only the magnitude change. Now you apply k larger than 1, the magnitude becomes larger, so apparently this crossover point is going to be what? It's going to be pushed to the left. Okay, so when you keep increase the k, what happens to this point? This point is going to keep pushing to the left, right? Okay, yeah, you see, now in the drawing, we assume that initially the crossover point is at the right side of the -1, 0 point. So you can have the margin to increase the k. Up to when you stop? Yeah, when you apply a k such that this point, what? It's right at the -1, 0 point. You see, this is the critical. Because if you keep increase the k beyond that point, then what? Then your crossover is going to be at the left of the -1 point. So your plot is going to go this way. What happened? What happened? You see, if the crossover point is here, your plot is going to go this way to close it. Okay? So -1, 0 point, it's outside your closed plot. No encirclement. Okay? No encirclement. Because we said the open loop system is stable. So if you don't see encirclement, yeah, closed loop system is stable. But when you keep, increase the k, push the crossover point to the left until you hit this point, then you increase further, what happened? Your crossover is going to have. Is going to be at the left-hand side of the -1, 0 point. And then if you draw the plot is going to go this way. What happened? Encirclement happened. So you can conclude it right away. The system will not be stable. Okay, you see, apparently, if we know this crossover point, then we should be able to know how much increase in the gain k, right? Okay, you see, this point actually give me the margin for how much gain k could be increased. So that's why we say this point is a gain margin, related to the crossover point. Okay, how to calculate it? I have the formula here. Okay, so I don't think I have the time here to talk about it. But anyway, before I let you go, I just want to point out another simple factor, and then we'll wrap up today's lecture. Okay. So the other simple factor is that let's see if we use a k to multiply k g of s. Let's see how this k is going to affect this crossover point. Okay. So like what I said, the k does not change the phase. So this crossover the point's phase is this angle, right? Okay. Let's say if it is a theta. Okay. You increase the k or decrease the k, it does not change this phase. The only thing you change is magnitude. So you're gonna see this point move along this line. Either goes to this direction or goes to this direction. Oh, you know what? It doesn't matter. As long as you move along this line, it doesn't matter. It does not change the phase. So you don't need to worry about that, right? Okay? Because you not move the plot to possibly encircle that, right? So that is why this point cannot be used to evaluate the gain margin. But this point makes a lot of sense to be applied to evaluate the gain margin. Okay, so I will stop my lecture here, and we'll continue on next Monday. So now, if you have any questions, you can ask it right now. Okay, we still have several minutes. Okay, no problem, Tara. Okay, okay. Any questions? Do you understand what I'm talking about here so far? No question. Okay, good, Andre. Okay. Okay. So, any question from other people? Okay, so if you do not have any more question, I will, just turn off the virtual lab, virtual classroom. Okay. All right. Okay. Yeah. You guys take care. Okay. All right.